Dr. Maxwell will rapporteur for this session.
Okay, thanks. Okay, so the first presenter is Mr. Ibrahim Mahmoud. And Professor Mabora said he is not there. So can we ask the technical team to play that video and then we'll try to follow it up. Thank you.
Hello, welcome. Today I would like to do my presentation on optical properties of antimony doped TiO2 compact layer deposited through deep coating. My name is Ibrahim Mahmoud. My supervisors are Dr. Robinson Usembi and Dr. Sebastian Maita. First, to understand what I'm doing, you have to understand the background of my research. Currently, there are two new types of solar cells: perovskite solar cells and dicensite solar cells. Both have shown to be quite good at collecting solar energy, well, with perovskite solar cells being far better, already surpassing conventional silicon solar cells at collecting solar energy. Its current architecture for perovskite solar cells is something like this. It's called the Msseesa perovskite solar cell. First of all, to be able to understand this, let's understand the basics for solar cell network. In a solar cell, we have the absorber layer in between. In the absorber layer, light comes in, it excites an electron, which creates an electron-hole pair. The electron moves downwards through the compact layer into the FTO layer, while the hole moves upwards into the whole transport layer into the metal electrode layer. In both cases, this creates the transporting the charge carriers out of the absorber layer, creates a voltage in the anode and cathode of the solar cell. This voltage allows us to create energy, to create electricity. In this perovskite structure, we have the perovskite layer as the absorber layer, the mesoporous layer and the TiO2 compact layer and the FTO layer as where electrons shall be transported out, the whole transport layer and the metal electrode layer where the holes shall be transported out. For the holes, if the holes and electrons are not transported out fast enough, they shall recombine. And they recombine that energy that could have been used to remove out of the solar that was gotten from the light. We lost through recombination losses. To prevent this, we use this mesoporous TiO2 layer. This mesoporous TiO2 layer allows the recently injected electrons to be removed out of the perovskite layer. Same goes with the TiO2 compact layer. TiO2 compact layer allows us to remove the electrons that have been created from the electron hole pair. So the purpose of this TiO2 compact layer, which is the center of our research, is the following. It provides good adhesion between the transparent conductive layer and the absorber layer. It provides good adhesion between this absorber layer, which is the perovskite layer, and the FTO layer, which is our transparent conductive layer. It acts as a hole blocking layer. In this case, when electron hole pairs are generated, you don't want the holes to exit to recombine with the electrons in this FTO layer. So to do that, the TiO2 compact layer needs to block holes passing through so that we can go through the whole transport layer, not through here. It acts as an electron transport layer. So the TiO2 compact layer helps transport electrons outside of the perovskite layer. It has a wide band gap, which allows light to pass through. So the TiO2 compact layer is expected to be transparent, so that when light comes through here, through the glass layer, you don't want the TiO2 compact layer to block light, which will be used by the perovskite layer to convert light to electricity. So compact layers are generally used in perovskite solar cells, dicensite solar cells, and organic light-emitting dyes. Making a defect-free compact layers chemical deposition process can be difficult, or even though such a method will be very cost-effective compared to physical deposition methods such as sputtering. A good Tier 2 compact layer should have the following properties. It should be uniform, it should be defect-free, and it should have high transmittance. That means it should be very transparent. And one way of improving current Tier 2 compact layers is by doping them with antimony. In previous studies, antimony doped Tier 2 has been shown to have good electrical properties compared to its undoped Tier 2 counterpart. In this study, we wish to experiment with antimony doped Tier 2 compact layer. We shall deposit this antimony doped Tier 2 compact layer using sol-gel method. Using deep coating method, which is a sol-gel method where the substrate is periodically dipped into a precursor solution, creating a film, which you can see here on the surface of the substrate. This film shall then be dried up and become a coating or a thin film. So our material methods. In the first step, we shall clean our substrate with ultrasonic cleaning. We shall use alcohol, ethanol, then we shall use acetone, then we shall use deionized water. Next step, we shall create our precursor solution. Our precursor solution will come in 5 different formats. First of all, to make our precursor solution, we shall mix ethanol, nitric acid, and deionized water according to this molar ratio, 40, 0.3, and 1. We shall also mix titanium hydroxide and ethanol according to this ratio of 1 to 80. The mixture of ethanol, nitric acid, and deionized water will be added dropwise into this first mixture. We'll have 5 different batches for different antimony concentration. Using antimony chloride dissolved in ethanol, we shall add a mixture of 0 mole concentration, mole percentage of antimony, mole percentage, which is the comparison between antimony to titanium. Comparison with antimony to titanium. So in this case, for example, it will be 0% moles of antimony compared to titanium, titanium dioxide, antimony chloride to titanium dioxide, so 0%. Then a second version shall be 1%, a third version shall be 2.5%, a fourth version shall be 5%. After this, the precursor solution will be mixed using a magnetic surf for 20 minutes. Then the glass substrate will be coated using deep coating. We shall vary the withdrawal speed to see how our coating shall come out, whether it should be uniform, whether it should be transparent, whether it should be defect-free. Then we shall anneal our thin film at either 400 degrees Celsius or at 600 degrees Celsius. To characterize our film, we shall do 2 things. We shall do thickness measurements using surface profiler and optical properties using UV visible spectrophotometer. So for results and discussion. In the first case, we measure the thickness of film using the surface profiler. Thickness of film is expected to follow the Landau-Levit equation. That means the thickness of the film shall be proportional to the withdrawal speed, which the thickness of film right here we can see is HO, and the withdrawal speed is UO. We did about 5 different, we had 5 different withdrawal speeds were selected. For 10 millimeters per second, 5 millimeters per second, 2.5 millimeters per second, 1 meter per second, and 0.1 millimeter per second. The film that was deposited at 1 millimeter per second was observed to be the most uniform and the least defect-free. So it was chosen for further optical characterization. The first optical characterization we did was just in the undoped TO2. In this case, you wanted to observe how different annealing temperatures shall affect reflectance. What was observed was annealing the film at 400 degrees Celsius showed a relatively higher reflectance than the film annealed at 600 degrees Celsius. In order to next, we calculated the refractive index of film from the reflectance data using this equation. We also calculated the porosity of our film from the refractive index using this equation. From here, we discovered the porosity of our film at 400 degrees Celsius was 0.3894. Porosity of our film at 600 degrees Celsius was 0.182. The film annealed at 600 degrees Celsius showed the lowest porosity. The reason for this is as the film was being heated up, the grains of the film began to expand. As they expanded, they got rid of the gaps between the grains. This in turn reduces the porosity of film. 0.182 is a relatively good porosity measure for a compact film. It's low enough. So next, we characterize transmittance of film for different antimony concentrations. Remember from before, the antimony doping was measured. So for the first one, we had a film that was completely undoped. There was no antimony flowed here. In here, we had 1% molar concentration for antimony. In here, we had 2.5% molar concentration for antimony, and then 5% molar concentration for antimony. So for our film with zero undoped TO2, it showed the highest transmittance. The second was our film at 1% antimony concentration. This showed lower transmittance, but it was still relatively high enough. As we increased the antimony concentration, the transmittance of our film reduced. The same was in our absorbance. The absorbance of our film increased with increase in antimony concentration. From our absorbance data, next we used this to get our tau plot, which we used to observe to find the optical band gap for our films. For antimony doping concentration of 0, the optical band gap was 3.201. This is the optical band gap of anatase thin films. So this was just what we expected. 3.2 was what was expected for TO2, anatase TO2 thin films. At 1% molar concentration, the optical band gap was 3.3038. It was much lower. And this went on. As we increased the antimony molar concentration, our optical band gap decreased. You can see that clearly here. It was almost linear. As we increased our antimony doping concentration, our optical band gap decreased. We can attribute this due to the antimony atom. The antimony atom has 5 electrons. The TO2 atom has 4 electrons. So when you dope antimony into the TO2 lattice, the antimony acts as an N-type doping. What this means is that the antimony shall add 1 electron into the TO2 lattice. This extra electron, valence electron, is easily excited. So when light is injected into the field, the extra electron is easily excited, so it jumps out of the existing valence electron and then comes back down into the antimony TO2 lattice. When it does this, the electron is excited. That excitement is then released in the form of light. So this changes the transmittance of film. It makes it more opaque. However, at 1% antimony concentration, the film was still transmittive. It didn't change the optical properties enough to make it transparent. With about 3.308, is considered transparent. So it wasn't complete. It didn't completely. It didn't affect the optical properties of a film in a bad way. Our conclusion is that the 1% antimicrobial concentration is still good enough to make a good compact layer, tier 2 compact layer. Thank you. That is all.
Well, thank you so much for that recording by Ibrahim, and it has taken 14 minutes. That's quite good. Now the recording has been shared by Dr. Odari, so we can download it and play and follow this presentation at our free time. Our next presenter is Gilia Sungi from UDCM. Sungi, are you around? Mr. Gilia Sungi from University of
I'm around.
Thank you. Please go ahead, introduce yourself and the topic, and then you will have 15 minutes for the presentation. Please go ahead. You can see your screen.
I'm presenting the effect of gallium doping on structural, optical transmittance, and electroconductivity of cadmium sulfide prepared by chemical bath deposition method. And the outline of the presentation is as can be seen on the screen. Cadmium sulfide, this is a semiconductor material which belongs to a 2,6 semiconductor family. It has got application in many fields, including it is applied in piezo transducers, and also be applied in photodetectors, and also can be applied in solar cells. Opening up of renewable energy has drawn the new research interest in cadmium sulfide due to its application in solar cells. Cadmium sulfide has been found to be reliable materials that can be used in thin film solar cells, which include the cadmium telluride, CIDS, and the CZDTS. Several attempts have been made effectively to replace cadmium sulfide as a window layer due to its cadmium content, but these have not yet still succeeded. Then still make this cadmium sulfide stand out as a potential material for application in solar cells as a window buffer layer. However, there are existing some major two problems when this cadmium sulfide is used as a buffer layer. Among those two challenges are high absorption coefficient and high resistivity. That high absorption coefficient, it causes the window absorption, in which it affects the short circuit current density of a cell. And again, high resistivity. High resistivity, when it is used as a buffer layer, this cadmium sulfide, high resistivity, it adding, it causes addition of high resistance of a cell. That addition of high resistance or series resistance of a cell, it just lowers the fill factor of a cell. So both affected the short circuit current of a cell, and the lowered fill factor just affect the overall conversion efficiency of a solar cell. Alternative is just, that there are some alternatives or just suggested solutions to these address the challenges. Among the suggestion is just to replace cadmium sulfide with the other window layer materials. We have said that still there have not yet found the material which are best than that one. So still the problem of toxicity, still that problem have not yet solved. But on the case of high absorption coefficient, it suggested that cadmium sulfide window layer should be considerably thin. But when it is too thin, it can cause the leakage in a cell. The leakage in a cell also can compromise the field factor. Again, alternative to that is just alloying and doping of cadmium sulfide buffer layer. To address the challenge on high resistivity, doping of cadmium with the proper or appropriate donors have been carried out, and the group of 3 elements have just shown an improvement on reducing the resistivity. However, in that group, group of 3 elements, it includes, say, aluminium, indium, boron, and gallium. Several research have been done on other elements, but there are few studies which have been conducted on gallium, and gallium shows that there is a promise that when it is doped on cadmium sulfide, it widens the band gap and also can reduce the absorption. So our interest was to investigate the effect of this gallium on how it can affect the transmittance of this material and also can affect the conductivity. The experimental setup to prepare the film was, as can be seen on a screen, and the precursor solutions were prepared from these sources, in which we varied the concentration of gallium so that to see the effect of gallium in cadmium sulfide buffer layer. And the findings were, we first want to see the effect of gallium if it can affect maybe the appearance. We found that the appearance of the cadmium sulfur does not being affected by the dopant gallium dopant, because when we varied the gallium concentration when we varied the gallium concentration with the same thickness of cadmium of doped gallium doped cadmium sulfide, the appearance of the sample remained the same. But this sample was prepared. This sample, which is seen to be different in appearance, the difference in appearance is due to the thickness. So we can say that the gallium concentration does not affect the appearance. Only the effect of gallium concentration on the solution was observed on the deposition rate. That when the gallium concentration was added, the deposition rate increased. As a result, the film thickness increased. That can be associated with the difference in ionic radius of gallium and cadmium. Since the gallium have got a small radius, it forms a strong bond between gallium and sulfur, that it reduces the evaporation of a sulfur in a bath. As a result, the film thickness increases for the doped film. Again, we did the analysis, we did the characterization of the prepared films, we did XRD characterization. These were the peak which was found for the prepared films, that the film prepared with the different gallium concentration. This was the concentration of gallium. This was for pure cadmium sulfur that was undoped. And we found that the spectral peak had a preferential orientation in this plane, which indicates that the prepared film had the polycrystalline hexagonal structure, and these were the peak. We also found that there were just some few peaks which indicate that there was a presence of cadmium oxide in the prepared film. That on our result, we found that the peak intensity for the film doped with this gallium concentration was large. That peak is associated can be associated with an improvement in the crystal quality of film prepared. And we observed a reduced interplanar distance for the film prepared with this concentration. And that reduced interplanar distance suggests that the gallium substituted the cadmium, that the topping was by substitution, which is just good, that the substitution of cadmium by gallium, it can increase it provides a free donor within the cadmium sulfide site, which is positive to the conductivity of film prepared. We also observed a slight increase in grain size for the doped films, which can be promising just good to the other properties like electrical and transmittance property. We did also a Raman analysis. We found that the doped film had high intensity, but we also found that there was a slight shift in the peak for the doped film. That slight shift in the peak can be associated by the incorporation of gallium in the cadmium sulfide site. Peak intensity for the doped to give us a problem that the properties of cadmium sulfide, like electrical and transmittance, are affected positively. We also did the characterization of the prepared films, that we found that this was for an doped film, and the grain size, the grains of the prepared film were uniformly distributed throughout the film, and they were mostly spherical in shape, and the grains size increased with an increase in property concentration. With the film prepared with this concentration had a large grain size, and also on the AFM characterization, we also observed a similar behavior, that the grain size increased with the gallium concentration. However, beyond 0.002 molarity of gallium, grain sizes decreased, which showed that there was a deterioration of the crystal quality beyond this concentration. We also did we used the UVVs lambda 19. Absorption age for the prepared film, these were the film prepared by varying gallium concentration. Absorption age was at about 500 nanometer, which implied that which corresponding to the banding up of cadmium sulfide. And the transmittance of the prepared film were increasing with the gallium concentration. However, the increase of this transmittance was not linear. That all of the prepared film had the weighted average transmittance of above 70, and the film prepared with the gallium concentration of 0.002 molarity had the highest transmittance of about 78. So we observed generally that there was a good shift in absorption age towards the lower wavelength, which suggests that the band gap of the prepared film was increasing with an increase in gallium concentration. As we have said, that the increase was not linear, that beyond this concentration, the transmittance decreased, similar that which reflects that also the band gap decreased. And this was the trend of the average weighted transmittance for the prepared film, of which this molarity gave us the highest transmittance. And the increase in transmittance is associated by the reduced scattering on the prepared film due to doping. We also that this is the banding up of the prepared film, in which the film prepared by this modality had the largest band gap, and this was a band gap, I mean the band gap of an optic film. So there was an increase in band gap with varying with increasing dopant concentration. And the increase in band gap can be attributed to most busting effect, which is the result of increased carrier concentration on doped film. We also did the characterization on the electrical properties, in which we did the whole effect measurement. We found that the carrier concentration of cadmium sulfide increased with an increase in dopant concentration. And above this gallium concentration, the dopant, I mean the carrier concentration decreased. That can be associated by interstitial combination. I mean interstitial combination of gallium into cadmium sulfide site. So interstitial, it means that there are potential barriers. I mean that there exist recombination centers in prepared film, and the film prepared by 0.002 molarity of gallium concentration, which showed the highest carrier concentration, suggests that the doping was by substitution. And the resistivity of the prepared film decreased with an increase and with an increase in gallium concentration, and on further increasing the concentration of gallium dopant, the resistivity increases. So generally, we can say that the doping of gallium, cadmium sulfide with the gallium concentration had an effect on the transmittance and electrical properties we have seen. That the optical transmittance improved. That can be associated with the improvement in optical transmittance can be associated with an increase in the band gap as a result of increased carrier concentration for the doped films. So gallium doping with this concentration is 0.002 molarity.
So your time is up. Can you wind up?
Then both the carrier concentration and the resistivity enhanced. That the prepared film had good optic and electrical properties that make it advantageous for application as a window layer. So we acknowledge these sponsors for my studies, DSM, Trust, ISP, Msseesa Network, Tanzania chapter, and thank you for your attention.
Thank you, Songi, for your presentation. Questions and comments will come later, so you have to wait for that. Now, our next presenter is Lilian Anyanga from University of Nairobi. Her topic is the effect of annealing and annealing atmosphere on the optical and electrical properties of CO2 germanium thin films. Lilian, are you there?
Yes, I'm there.
Please go ahead and share your screen. You have 15 minutes for your presentation.
Okay, thank you. Are you able to see my screen? Hello, are you able to see my screen?
Yes, we can see your screen.
Okay, thank you. My name is Lilian Owino, MSc student from the University of Nairobi. And today I would like to share with you on the effect of annealing ambient on the optical and electrical properties of TiO2 germanium thin films for photovoltaic application under the supervision of Dr. Waita, Professor Msembi, and Professor Nyongesa. So on our introduction, the study of thin films, that is both theoretical and experimental, has led to a lot of scientific and technological interest. And this is because of the unique optical and electronic properties these films exhibit or possess. And the knowledge gained from such research has been applied widely in a lot of sectors, such as communication, transportation, and even industrialization, just to mention a few. And it is expected that these applications are likely to broaden in the near future. And thin films from the transition metal oxides, such as titanium dioxide, zinc oxide, you can talk of copper 2 oxide, have been the center of research for quite some time. And this is because these metal oxide show good mechanical and chemical properties, and they also hardly deteriorate. Titanium dioxide semiconductor, which has been the focus of our study, has attracted great attention from many researchers, and this is because of its unique characteristics, such as its high refractive index. It also shows a good, excellent transmittance in the visible region. It also has good thermal and chemical stability. It is non-toxic. And also it's abundant on the Earth's surface, which means it's affordable to many researchers. So the semiconductor exists in 3 crystalline phases. We have anatase, rutile, and bruchite. The first 2 have got a tetragonal structure, and bruchite has got an orthompic structure. And all these phases can be readily prepared in our laboratory. Optically, we can categorize this semiconductor as having a high transmittance of greater than 80% in the visible region. And it also has a wide band gap of 3.2, 3.0, and 3.2 for anatase, rutile, and bruchite, respectively. And electrically, TiO2 is characterized as an N-type semiconductor, and this is because of its oxygen deficiency. Titanium dioxide has been applied majorly in optoelectronics, and here we can see some of its application in smart windows. We have LEDs and in solar cells as a photoanode, which is the main application of our films. Sorry for that. Titanium dioxide has been faced with some 2 major limitations. One of it is the recombination of photo-generated electron-hole pair, which generally reduces the overall efficiency of fabricated solar cells. And again, being a wide bandgap semiconductor, titanium dioxide can only be activated using radiation from the ultraviolet region. And as we know, ultraviolet accounts for less than 10% of the solar spectrum. So there is need to broaden the spectral response to the visible region. That is so that we can make use of the solar energy. Now, researchers have come up with a number of ways to counter the shortcomings, and among them is the use of dopants. We can talk of dye sensitization, some form composites, and also we have this aspect of introduction of titanium ion and oxygen vacancies in TiO2 structure, by annealing these films in oxygen deficient environment. Now, the first two, doping and dye sensitization, have proved to be effective, yes, but again, some of the dopants, especially the transition metal oxides, still acts as sites of recombination. And also some of the dopants cause thermal instability in the TiO2 structure. Other dopants also result into photocorrosion in the material. And also the instability of the organic complex in the dye, and also the charge transport still poses a major challenge. So in our work, we have tried to make defective TiO2 by making TiO2 germanium composite, and also introducing titanium ion and oxygen vacancies by annealing the films in oxygen deficient environment. So our major objective of this work is to investigate how the annealing ambient or atmosphere and the germanium concentration affect the optical and electrical properties of TiO2 germanium thin films for photovoltaic application. On our methodology, the materials that were used in this study, we had pure TiO2 and TiO2 germanium composites discs of ratio 95:5, 90:10, and 85:15 with 99.99% purity. And we used fluorine-doped tin oxides as our substrates. So before deposition, our substrate, we cleaned our substrate using the standard cleaning procedure as shown in this figure 1. And then radio frequency magnetron sputtering was our deposition technique. We deposited the films for 1.5 hours using, under optimum power of 220 watts and argon fluoride of 35 SCCM. So this is the radio frequency method, sputtering method that was used. Here is where we place our targets at this point, and then the substrate is placed at this upper point. So, and then we have our gas inlet here. Of course, our gas was argon. So basically, this is just a plasma-based deposition process in which energetic particles in form of ions, photons, neutrons are accelerated towards this target, strike it, releasing materials in form of vapor. And then these materials travels in this vacuum and condense on the surface of this substrate to form a film. It is a good method because we expect no or minimal contamination of the film because the whole process is carried out in the vacuum. So after deposition of our films, the films were annealed in 3 different atmospheres. We have air, argon, and nitrogen. And this is a 2-dimensional tube furnace that was used for heating the films. So the respective gas was allowed into the tube, and here is where we place our sample, of course. So it was allowed into the tube at around 20 ml per minute during this deposition process. And the annealing process was done for 1 hour at 450 degrees. For 450 degrees. Looking at our results, the transmittance, these are the transmittance spectra for pure TiO2, the first 3. And then we also observe here down here we have other graphs, 3 of them. For TiO2 germanium, ratio 85:15, annealed in 3 different atmospheres, that is nitrogen, argon, and air. Note that I was not able to show for TiO2 germanium annealed in, ratio 95 to 5 and 90 to 10, but take note that they have a similar behavior as these ones, the ones that are shown down here. They behave in a similar way. So looking at these transmitters, we can notice that the films annealed in nitrogen. For example, TiO2 germanium annealed in nitrogen, the pink one, as well as the black one for pure TiO2 annealed in nitrogen, as this key directs us. We notice that the films annealed in nitrogen recorded a lower transmittance. And this could be attributed to one, an increase in the film thickness, and two, this one could be associated by the color change that turned dark brown when we annealed these films in nitrogen. We know that a dull color suggests a high absorption in the visible region, and therefore this could also have led to the lower transmittance for the films annealed in nitrogen. On this other spectra, we have different concentration of TiO2 when germanium was added into its matrix. So we have 5%, 10%, and we also have 15% germanium concentration in TiO2. I have also taken just one spectra for the films annealed in nitrogen. And you also note that for those other films annealed in air and argon, they also behave in a similar way. I mean, the arrangement of the spectra is almost the same. So we notice that we have an increase, we have a decrease in transmittance as we increase the concentration of germanium. And this is because of, again,
can you try to wind up?
Again, it's because of the increase in the film thickness, and also it could be because of the increase in the film roughness, which could lead to a scattering and therefore lowering the transmittance. This is the energy band gap for the films annealed in 3 different atmospheres with different concentration of germanium. It is noticed that as we increase the germanium concentration, we notice that the band gap also decreases up to around 10%. And this could be associated with the increase in the particle sizes, as confirmed from our X-ray diffraction results, which I may not be able to share because of time. We know that crystallite size have an inverse relation to the band gap. So this implies that as we increase the crystallite sizes, or as the crystallite sizes increase, we expect the band gap to decrease. But further increase in the germanium concentration for 15%, we notice that we have a rise in the energy band gap, and this could be attributed to the low number of localized states in the TiO2 structure, leading to an increase in the band gap.
Lillian, please summarize. Your time is over.
Yes, I'm finishing, yes. And then this is the electrical resistivity. We notice that we have a decrease in the resistivity once we anneal the films, and also the films annealed in nitrogen recorded a lower resistivity. And this is because of development of oxygen vacancies, which acted as donor centers for electrons. And also we had a decrease in the resistivity as we increased the germanium concentration. And then in our conclusion, we found out that the films annealed in oxygen deficient environment showed a better conductivity with a narrow band gap, and also a lower transmittance in the visible region, and also increase in germanium concentration led to a decrease in transmittance, energy band gap, and resistivity. And our good films were obtained at optimal condition 10%, germanium concentration, and of course, an yield in nitrogen. Thank you for your time.
Thank you, Lillian, for your presentation. I request that you stop your screen sharing so that the next speaker can take over. Now, our next presenter is Emmanuel from University of Dar es Salaam. Emmanuel, are you there? Emmanuel from UDCM.
Yes, I'm connecting.
Yeah, please go ahead, share your screen, and you have exactly 15 minutes for your presentation. Thank you.
Okay, I will proceed just like this.
Yeah, please
I'm
proceed.
Olotu Emmanuel from the University of Dar es Salaam. I'm in my PhD. My PhD is in progress. My supervisors are Dr. Mnyuka and Dr. Samiji. I'm presenting to you the work entitled Effects of Annealing Temperature on a room temperature. This is part of the zinc oxide for CZTS solar cell. CZTS is an abundant and low-cost materials, making the solar cell from this material potential for low cost. But also is a thin film solar cell, so it makes them even low cost, provided few materials are used. Here we report the properties of zinc oxide deposited at room temperature, and then rapid thermal annealed at varied temperature. The motivation of doing this work, there are a lot of work on zinc oxide. But the motivation of this work is to just understand, it's just to see if the mechanics of zinc oxide properties during annealing may have influence on CZTS solar cell. So we wanted to understand that. And this one is the cartoon that shows the structure of CZTS solar cell. The CZTS here is working as the absorber, and the zinc oxide that we are depositing is working as a window layer. Okay. So these are the deposition parameters used. We deposited the zinc oxide on a soda lime glass using DC sputtering. Glass were cleaned using ultrasonic machine in a DI water for 25 minutes, and then it was left to dry in air. Then we sputtered the zinc oxide at room temperature using the parameters that are shown below here. The base pressure, working pressure, power is 175 watts, argon flow was 50, ECM, oxygen was 50, so 50. Then we sputtered for 10 minutes. Then we took the sample and annealed it in an annealing machine, RTP machine. The wrapping rate of the RTP machine was 20 centigrade per second. That was very, very fast annealing. We are using this fast annealing because we avoid loss of, the CZTS has the tin, which actually evaporate very fast if you anneal for longer time. So that's why we use very, very high speed wrapping rate. Then we anneal it at different temperatures, as it is shown here in the results. Here I'm presenting the XRD results. We have not yet indexed the peaks, but actually we saw that there is a general decrease of the grain size with the increasing temperature. This grain size were calculated using the Scherer formula, and we saw that as the temperature increases, the annealing temperature increases, the grain size also generally decreases. But also we saw that there were kind of were also a shifting of the intensity peaks with increasing temperature. Though that was not there was no clear trend, but actually those at lower temperature had the peak intensity was at lower angles, but at higher temperature, since that the intensity peak, the position of the intensity peak was also increased. We also checked it for the SME for lower temperature and higher temperature. It's 100 centigrade and 300 centigrade. And we saw that the grains get shapes as the temperature increases, which is expected. But with the low temperature, we saw that the grains were not well defined as compared to that at high temperature. We also measured the solar transmittance and the average, and then we computed the average transmittance, and we saw that the solar transmittance of the sample increases with the increasing annealing temperature. Is also expected. Up to 200 centigrade, we might have a very good applicable sample for CZTS, because you can see the transmittance is almost 80%. Then we also computed the band gap of these materials, of this zinc oxide, and we saw that at 200 centigrade, the annealing temperature, we get at least closer to the reported band gap of zinc oxide, which is 3.5. So we consider the 200 temperature to be a good temperature for, might be good temperature for this this sample or this zinc oxide. Our conclusion, that's what I've said, but this needs to further apply it in a CZTS solar cell so that we can see whether these changes in the properties of zinc oxide will have an influence on the CZTS solar cell itself. Thank you very much.
Hello.
Yes.
Yeah, thank you, Emmanuel, for that presentation. Now, we are going to take time to welcome questions, comments, or any form of discussion to improve this work.
Can I ask a question, please?
Please go ahead. Tell us your name and which institution you're coming from.
Yeah, I'm Professor Samir from the Technical University of Kenya, and I like the presentation. It shows experimental investigative research, but what I'm asking is how do these results compare to what is out there in literature, like in terms of what others have done? Have you been able to validate your results with others so that to get a good corridor in terms of comparison? Thank you.
Thank you, Professor Samir. I think your question cuts across all the 3 or 4 presenters.
Yes.
So, any one of those presenters, please go ahead and give. Can you respond, please? Emmanuel, do you have anything to say? Or Lillian? Hello?
Oh, okay. Okay. I agree that I didn't put some reference here to compare what I'm getting from, I mean, what is in the literature sample, but it's just because I had a limited time to do so. But generally, the result for zinc oxide, actually, they are not very far. As I said, for example, for the band gap, the band gap for zinc oxide has reported 5. I find that in the literature. So what we are getting is not very far from the literature. And I think I will enhance that in my presentation.
Thank you, Emmanuel.
Yes, I think I have responded.
Thank you.
Yeah, even the solar transmitters, it's around 8, which is also suitable for application. It's not very far from what is reported in the literature.
Okay, can we pick any other question or comments?
Yes, I have a question.
Please go ahead.
This is Jorim Obila from University of Nairobi. Now, for the current presenter, I'm a little bit confused because I heard him talking about tin at some point, and now eventually it now turns to be zinc oxide all over. So maybe you try and explain that. And in your explanation, there's a point you said tin evaporates at some temperature after annealing for some time. How did you validate that? Then for the presenters, Lillian and Ibrahim, for Ibrahim, this is my question. What were you aiming at when you are adding antimony to titanium oxide? Because from what I can see, the band gap of titanium oxide, if you added antimony, reduced to around 2.8 or something like that, which means the absorbance of that layer will go to even that the visible region. And as you know, if we are using, or if you are using it for solar cell applications, we need much of the light or much of the visible part of the solar region or solar spectrum to go to the absorber material. So if we are trying to block part of the visible region, what are we trying to do to the solar cell? Are we reducing the performance? Or maybe what was the importance of your antimony? And then for Lillian, also we have seen germanium is reducing transmittance of titanium oxide. What is the role, or why is it important in this research? Thank you.
Thank you, Jorem. Now, I think Lillian and Emmanuel will answer your questions, but Ibrahim is not. No, I can hear some background noise from Emmanuel. Emmanuel, can you mute your mic? Technical team, can you mute most of people's mic? Thank you. Lillian, can you go ahead to answer?
Wow. Okay, thank you for your question.
Mimi.
Hello.
Go ahead, Lillian.
Yes.
I think Munala is making a lot of noise. So maybe Munala can keep quiet. Munala and maybe the group. Okay, Lillian.
Thank you, Jorim, for your question. When we were looking at the limitation of TiO2, I did mention that it has a wide band gap, which means it is majorly activated by radiation from UV light. And we know that UV accounts for less than 10% of the solar spectrum. So this will limit the practical efficiency of solar application. And therefore, we need to reduce the band gap so as we utilize the visible light. So germanium, it's just actually helping us to lower the band gap of TiO2. But again, we are not saying that we shall add a large concentration of TiO2 so that we actually minimize, we lower to the transmittance to unexpected levels. So we're just using some little concentration of TiO2 so as it helps us reduce the or lower the TiO2 band gap. Yeah, thank you.
Okay, thank you, Lillian. Now, Emmanuel, there are questions which Jordan posed to you. Can you please respond? Emmanuel, are you there?
Yes, I'm here.
Yeah, please go ahead and respond.
I think I will comply. I will send the, I think there is a request to send the presentation, right? Yeah, that one I will send. I think there's, okay, we'll go to here. Okay, I will send the presentation, no problem.
No, it's not about the presentation. He asked you a question that you talked about zinc oxide and then you talked about TiO2. I think there's something related. How do you mix the two? I think I didn't get it well, but that's the question should be around that area. Yes. Jory, can you please repeat your question, Manuel?
Oh, okay. Okay. I think this question, okay. How did you arrive at the base pressure of 5 millibars and which equipment did you use? We used the sputtering unit, bars 250. We pumped it down for several, like 3-5 hours to achieve that 5 millibars. And yeah, I think I have responded to your question.
Okay, thank you. Thank you so much. And if there's no any more question, I want to thank all the presenters, and I hand back to the chair.
I have one.
Sorry, see, how did you arrive? May you restate your question, please?
I think you are experiencing network problem. Maybe we just go ahead. I can even post you the question in the chat. No problem.
Okay, thank you, Jordan. And I was saying, in case there's no any more comment, I would like to thank all of you for this session, and I hand over to Professor Julius Mabora. Please, Professor Mabora. He's not in.
Hello, I want to thank everyone for this session. The chair of the session, Dr. Karideo from Makere University, and our rapporteur, Dr. Mageto.